Okay, so today we are going to talk about functions. Up until now we've discussed equations and different types of equations, and we haven't really come down to what is a function. And I know you guys have probably already seen this definition, but we're going to take all the relationships for math and categorize them, and one of the main categories is the category called functions. Here's what we're going to learn. By the end of this lesson, you should know how to determine whether relations between two variables are functions or not. You should be able to use function notation and evaluate functions, and that's a basic skill that you learned in Algebra 1 and Algebra 2. You need to learn to find the domains of functions, a skill you learned in Algebra 2. You need to use functions to model and solve real-life problems, and then a new skill for us, evaluating difference quotients. So let's first introduce you all to functions. The definition of a function. Now, a function is a special category of relationships. And we define a function from one set of variables to another set of different variables as something is a function if each element in one variable is assigned to another element, to exactly one other element in another set, okay? So each element in A goes to one element in B, okay? So I don't have an element in A going to this element and this element. This element in A only goes to one in B. Now, that's not to say that two different elements in A can't go to the same one in B, okay? So, set A is called our domain. That's our inputs, okay? And set B is our range, which is our set of outputs. Now, set B, and this is very important to note, all the elements in set B do not have to correspond to something in set A. See, we have a few elements in B that don't correspond to anything, okay? And that's an important distinction that as you get further along in math, you'll see happen again and again, okay? So every input of A has one output in B. So characteristics of a function, we've talked about this. Each element in A must be matched with an element in B, a single element in B. Some elements in B may not be matched with any element in A. Two or more elements in A may be matched with the same element in B, and we saw that in our picture. And an element in A, which is the domain, cannot be matched with two different elements in B, the range, the output. We have four different ways to represent a function, and we've talked about this before verbally. And that's by a sentence that describes how our input variable is related to our output variable. Now, sometimes this is, like a word problem or a situation or that type of thing. We can describe it verbally. We can also describe things algebraically, and that's with an equation in two variables. So f of x equals 3x plus 2 or something like that. Numerically, that's by a table or list of pairs that matches input variables and output variables. And what I'm thinking here is, either coordinate pairs, x comma y, or like a table of values like that. And then, of course, graphically, which is by points, taking our numeric values and putting them in a coordinate plane, not plan, in which the input values are represented by the horizontal axis and the output values are represented by the vertical axis. So, when we're testing for functions, we need to determine whether the relationship represents y as a function of x. Now, in our case, we define functions as a and b. I wrote that too big. A and b. And in this case, b is our y and a is our x. So remember, we had every element in A going to an element in B, and we would have said that B was a function of A. Okay? Now, an element in A can't go to two different elements in B, or it's not a function. Okay? So, we're looking for, do we have any x values that go to more than one y value? Well, when we're looking at tables, we can see on a table here each x value has only one y value. So yes, y is a function of x here. But on the second table, 2, that's the same number, goes to two different values. It goes to 1 and to 2, so no, this is not representing y as a function of x. Okay? Now when we're looking at this graph, y, remember, is our vertical axis and x is our horizontal axis. So we cannot have any x value on any value of x that has more than one value of y. Now, if I look on this parabola, each x has exactly one y. Okay? Even down here, they have exactly one y. There's nowhere on this parabola that I can find each x having more than one y. So yes, y is a function of x here. Now, when I go to this ellipse, however, if I pick the value of x as 1, or 0.5 there, I guess it would be, I can see I've got two different values of y here. So each x here has more than one output. Each input has more than one output, okay? And so therefore y is not a function of x. Do they still have a relationship? Yes. However, it is not the category that we call functions. So testing for functions algebraically, which functions represent y as a function of x? Okay? So to do this, what we do is we try to see if we can solve for y, to get y all by itself. Okay? So here we can take and we can subtract x squared. So we get negative 3y equals negative x squared plus 4. We're going to divide by negative 3. So we get y equals x squared over 3 minus 4/3, right? So I can take each x and I can show that it only gets one y. Okay? Now, I can see that this is going to be a quadratic relationship. Okay? I've got an x squared. And we know that x squareds produce parabolas, and we know that parabolas have one input, each input having only one output. Okay? But I could see that if I graph this as well. Okay? Numerically creating the numbers and then graphically putting them on a coordinate plane. Now, this next one, if I get y by itself, I'm going to subtract x, and I'll get y squared equals negative x plus 1. Okay? So, if I look at this, and if I get y by itself, and I unsquare this, by taking the square root of both sides, I would get y equals the square root of negative x plus 1. But let's look at what's going on with this middle step here. I'm saying that I take a negative x, or an x, I put it in there, okay? And let's let that x be 3. So I say that I've got a y squared equals the negative of 3 plus 1. Well, the negative of 3 plus 1 is negative 2. So I'm going to say y squared equals negative 2. Can I square something and get a negative number? Well, no, I can't. Okay? And in reality, what this is going to look like is it's going to be a square root function that has some shape that looks like this. Okay? So, and that's not the exact shape because I haven't, but it's going to be one of those type things. Okay, but there's no way that I can square something and get a negative number. So this is not a function of x. Okay, but yes, y is a function of x on this first one. And we'll go through some more of these in class so that you have a better idea of this. Function notation, this is review. Remember, say we have f of x equals 2x plus 3. Our function name is f. Our input variable is at x. And then, of course, our function definition is the rest of this. When we're evaluating a function, we take whatever is in place of the x as our input, and we substitute that into our function definition. So if we have g of x equals 2x plus 4, and we want to find g of 1, we're going to substitute 1 in for x, and that would be 6. G of t, that would be 2 times t plus 4. G of t plus 6 would be 2 times t plus 6 plus 4. And that would require a little simplification, because that's really 2t plus 12 plus 4, which simplifies to 2t plus 16. Okay? So it's okay if what's in place of our x is actually an expression, and we're going to use that later on in the course, in the lesson today. Evaluating a piecewise function. Now, piecewise functions occur, and actually there are a lot of real-life functions are piecewise functions, because you might have a situation where part of a function is described by one type of relationship, and that would be this type of relationship, and the other part of the function is described by that type of a relationship. And they have a definite starting and ending point between the two different relationships. Okay, so in this case we need to look what's our input, and which of these categories does it fall into? Well, we've got -3 here, and 0 is our dividing point. -3 is less than 0, so we're going to use this top function. So f of -3 would actually be -3 squared plus 3 times -3 minus 1, which is 9 minus 9 minus 1, which is -1. Now f of 6, however, is greater than or equal to 0, so we're going to use the second definition. So f of 6 will equal 2 times 6 minus 1, which is 11. Okay, what happens if you've got something on the dividing line like f of 0? You have to look and see where is it greater than or equal to 0. This is the or equal to part, so we would have f of 0 equals 2 times 0 minus 1, which is -1 again. The domain of a function. Now, we have a couple of concepts here. The domain can be expressed explicitly, where we name the set of all numbers in the domain, like give you a list, or implicitly by giving an expression to define the function, or an equation to define the function. Okay? So if I give you a set of coordinate pairs, or a list of inputs and a list of outputs, that's explicitly naming all the numbers in the domain, okay, or range. Implicitly is when I just give you something like this, okay? So the implied domain includes all the numbers that can be used as inputs for which the function expresses the output as a function of the input. Thinking of it as, say, we want to know what can I put into this function without breaking it, is how I like to think of it, okay? And there's two different situations where you can essentially break a function, where you can cause it to have outputs that don't exist. Okay? One of those is if you try to divide by 0, and the other is if you try to take the square root of a negative number. Okay? So let's see. If I were to divide by 0 for this first one, I would have to be asking what would cause this to be 0. Okay? So x minus 4, how would that equal 0? What x's would cause that to equal 0? Well, adding 4 to both sides, I could see that if x equaled 4, then this bottom would equal 0, right? We can see that by saying 2 over 4 minus 4 is 2 over 0. So that number cannot be in our domain. Otherwise, y is not a function of x. So x cannot equal 4. Now, for square root functions, we have to say what causes what's under that square root to be greater than 0. Okay, so that 2x has to be greater than 6. Dividing by 2, x has to be greater than 3. Okay, so in the reciprocal function case, we're stating what x can't be. In the square root function case, we're saying what x can be. Now, we could use set notation, and we'll discuss that in class, to always describe it as what can be in the domain, but we'll go into that later. So let's find the domain of each function. Here we have an explicitly defined function for this top number. Okay, the domain is all of our x values. So my domain is the set of 2, 3, 4, and 5. And there I've explicitly listed my domain. Now, for this second one, my input value is my r, right? That's my input variable, not value. Can I square any number? Well, of course I can, okay? So since I can square any number and always get an output, I don't have any domain restrictions. So my domain is the set of all real numbers, and we abbreviate that with a double-barred r, and that just means the set of all real numbers. Okay, applications. Jill kicked a football down the field. The path of the football can be defined by this function here. And here we see this function graphed out. And I want to know, what is the domain of this function? What are my input values? Well, we know that inputs are graphed on the horizontal axis. So we can see that even though this function is defined before 0, we know that we probably didn't, we have to think of what this represents. This bottom thing here is actually time. Top is height. Okay, so time, we're not going to go back in time. So time actually, the function doesn't start until 0, 0. So even though mathematically it exists over here, in reality it doesn't. So my domain is all x's the set of all x's such that x is greater than 0, greater than or equal to 0, and less than or equal to, and here's where it stops, at 93.1. Okay? So that's how we're going to write this. Okay? So the set of all x's, where x is between 0 and 93.1. Difference quotients. This is the final thing that we're learning here. One of the basic definitions in calculus employs this ratio. And this ratio asks us to input x plus h into our function and x into our function, subtract the two, and then divide them both by h. Okay? Now, that means that h can't be 0. So 0 is not in our domain of this difference quotient. Let me erase this so that we can clearly see how we're doing this. So first thing I'm going to do is I'm going to input x plus h. So I have x plus h squared plus 5 times x plus h minus 1. And then minus all of f of x, which is just x squared plus 5x minus 1. All of that divided by h. Now I've got some math to do here. Simplification. I've got to square this, distribute that, and then distribute our little friendly invisible -1 here. So using my perfect square trinomial shortcut, I'm going to multiply this out as x squared plus 2xh plus h squared. Distributing my 5, I will have plus 5x plus 5h minus 1 minus an x squared minus 5x plus 1 all over h. Now, you're probably going to need to stop this video and catch up. That's fine. Now we have to look and see what do we have. We have an x squared and an x squared and negative x squared that cancel out. We have a 5x and a negative 5x that cancel out, a negative 1 and a positive 1 that cancel out. And so we just have a few terms left, which are going to be these two terms and this term. Okay? So we have h squared plus 2xh plus 5h, all divided by h, right? Now what I notice here is that all the terms in the top have an h in them. So I'm going to factor out an h, and I get h plus 2x plus 5, all divided by h, which simplifies out to h plus 2x plus 5. Okay? So, by now you should know how to determine whether relations between two variables are functions, use function notation to evaluate functions, find the domains of different functions, and use functions to model and solve real-life problems. And we've also shown you how to evaluate difference quotients. See you in class.